regarding the process material. And you will ask me, Eugene, what are we going to look at? We're going to look at Johnson-Cook equation again. Okay, we're going to apply Johnson-Cook equation in this again. Okay, on how, I say it again, on how to select process parameter. Interesting, isn't it? Okay. So don't forget what you learn. Okay, don't forget what you learn. We're going to apply more of it. Right. So I'm going to talk briefly about what are the some of the metal cutting processes. So you guys have seen turning already, right? So we have metal cutting process. The metal cutting process includes turning, we have seen it, drilling, milling, tapping, sawing, broaching. Okay, is there any that's it? Okay, right? So all this turning, drilling, milling, tapping, sawing, broaching, all of them will always have all these variable to control. Okay, rake angle. Okay, you also can have to control cutting edge radius, tool material, nose radius, approach angle. Okay, so all these have all these characteristics. Okay, but the most common one is the shear angle, which is not written. The shear angle. Okay, so all these processes have shear angle. Okay, later on we'll see why shear angle is so important. Okay, so the first thing we're going to talk about now, okay, we're going to draw the turning process. Okay, so let me talk about turning process. So when we go into turning process, then we talk about how to do control process parameter with Johnson-Cook equation. Okay, let's look at turning operation. Okay, turning. So in turning, like what we've seen in the video before on YouTube, you have a workpiece over here. All right. So if I were to draw my transformation, this is X, Y, and that is my Z. Okay. So the workpiece will be rotating. Okay. And this arrow represents U. And you guys know by now, U is our cutting speed. Okay. So how fast the material move is by controlling the RPM, or revolution per minute. Okay. And then this is our axis, the workpiece. So now the workpiece is moving. Okay, so this is our workpiece. Then we have our tool. Okay, so I'm going to draw our tool. So this is our tool. Right? So our tool also have a motion. So this is our tool motion. Okay, so the tool motion is parallel to the x-axis. Okay, so this is our motion. Right? So this is our feet direction. Okay, that's our feet direction. So the feet direction correspond to our undeformed chip thickness. Okay, so the tool is moving in a linear motion, right? And then the workpiece is rotating. Right, the workpiece is rotating, and then the distance from here to here, okay, the distance that the tool move This is known as our depth of cut. Okay, that is our depth of cut, which you can see down here is also known as our width of cut. Okay, so the axis that I've just drawn down here, that is known as our neutral axis. So everything is rotating, the neutral axis is not rotating. So that's our neutral axis. Okay, so now let's look at some of these feet, okay, cutting speed. How can we control them? Okay, so the cutting speed, let me get rid of this. So I'm going to use a lot of that diagram. Okay, so let's look at cutting speed. Okay, so the cutting speed range, this is about turning, yeah, range between 0.5 to 5 meters per second, depending on the workpiece material, and it is controlled by the strain rate, right? You guys seen this, like, whoa, seen this before. Strain rate sensitivity of the material. Okay, that is the cutting speed. Okay, the depth of cut. So next we are going to talk about depth of cut. Or width of cut, right? It's controlled. So the range, okay, the range 0.1 millimeter, and I've seen as high as 2 millimeters. Okay, so the width of cut or depth of cut is controlled by the use strength of the material and also the rigidity of the machine. The machine 2. So machine 2 over here for turning is the lathe. For turning. Okay. So that is the depth of cut, width of cut. And then the feet, right, the feet or undeformed chip thickness, right? The feet or undeformed chip thickness. So the range is between 0.05 millimeters per revolution, and it can go up to 0.4 millimeters per revolution. Okay, and this is controlled by the surface roughness Okay, this is controlled by the surface. So depending on what roughness you want to generate, I will tell you later why the roughness will come into play. Okay, that's generated and by the strain hardening behavior of the workpiece material. So you come and see, you realize another term again, right? Strain hardening. Now, if we were to go back to strain rate of the material, I like to also add thermal softening. Okay, the thermal softening also play a part on your cutting speed. Okay, okay, and then we're going to write. Okay, so turning. Okay, so when do we use turning? But before I go on, you can observe a few terms that you've seen before, right? So it depends on the use strength. The use strength in Johnson Cook is our A, and this is controlled by our strain hardening behavior. This is your B and N. It controlled by your strain rate. This is C. Thermal softening is your M. Okay, here we go again, right? So when do we use turning? So most of the time we use turning to generate. Okay, we use turning to generate round features, cylindrical features. Okay, so turning. Okay, turning is used to produce. Okay, cylindrical features. If it's not cylindrical, you cannot use turning. Okay, you have to use milling. This is because of the nature of the process. Is that the workpiece is spinning, right? Now, if we were to view from another view, all right. So now we are going to do not the front view, but the side view. What I'm trying to do is I'm trying to highlight why the feet can control the surface roughness. Okay, that's what I'm trying to elaborate down here. Okay, so if we now draw our transformation now. Okay, so the transformation is relative to what we have drawn before. Now we are viewing this x and y. Okay, so over here, this is my neutral axis again. Okay, there's my neutral axis, and this is our workpiece. Okay, so this is our workpiece. Then our workpiece come to here, right? Stop over here, and then I'm going to draw our tool. Okay, so this is our cutting tool. Yeah, this is our cutting tool, right? And then this is our workpiece over here. So now the workpiece is rotating, by the way. Okay, the workpiece is rotating. Okay, then it comes down over here. Okay, so when it comes here, okay, it comes here. I think you cannot take so deep of an undeformed cheek thickness. Okay. Okay, so over here you have our shear angle, right? Then you have our chip. Okay, so this is our chip. This is our tool, right? And then this is our small t, right? Look at the small t. So that is our undeformed cheek thickness, right? Small t. And then over here, this angle over here, that is our shear angle. Okay, so now I'm going to draw. Okay, I'm going to draw another feature over here. Okay. Yeah, so I'm going to so the feature I'm going to draw is I'm going to draw some straight lines. Okay, I'm going to draw some, and this straight line is in vertical orientation. Okay, I'll draw a few. Oh, this is too wide. Okay, so I'll draw them down. Okay, that's enough. So each step across is controlled by your undeformed chip thickness. So the distance between here to here is controlled by your what? T. The smoother you want your workpiece in the end, you have to